Hello, Chem 1. Okay, so here's a hope that third time's the charm. This will be officially the third time that I have tried to videotape this PowerPoint presentation. First two wonked out as they tried to export or save. So let's cross our fingers for this one. This is the last PowerPoint of the stoichiometry section, and where we're going to be touching on a topic that's called limiting reactants. And you'll see what that is as we go on. So it still falls under the big picture of stoichiometry and what it means when you're trying to determine the amount of reactants needed or the amount of product that's going to be made. We're going to focus a lot more on the amount of product that can be made in a chemical reaction when we know something about how much of the materials are there. So let's start with a little bit of a review. This is a mass-to-mass example, and we're going to use this as a springboard to what we're going to talk about that is new today. And this is very typical of what we did about 2 weeks ago. It says, what mass of aluminum oxide is formed when 124 grams of aluminum reacts with an excess of iron 3 oxide according to the following balanced chemical equation? Now, I'll remind you what that in excess means. With the excess means I have more than enough iron oxide to react completely with the aluminum. So what we've done in the past is say, well, don't worry about how much iron oxide you have. You know you have more than enough. So just focus on the one thing that they gave you information about. So how would we solve this problem? Well, first thing we need to do is get our given and our unknown. Our given is 124 grams of aluminum is how much was given to us. And then our unknown or asked for is we need to solve for the mass of aluminum oxide. And we know that we do that when we get that in grams. The next step to explicit method is to actually come up with a plan. Let's think about how we would solve this problem. So if we look at our mole diagram, we know that we're starting over here in mass. And we're ending up, so that's the mass of aluminum, and we know that we're going to end up with mass of aluminum oxide. So we need to go from mass to mole of aluminum, that won't work, put Al here, to mole of aluminum oxide, to moles of aluminum oxide to mass of aluminum oxide, and voila, we have a plan. We have a way that we're going to go across and solve for our problem. So our plan is a mass of aluminum to moles of aluminum to moles of aluminum oxide to mass of aluminum oxide. That's our plan. So let's see. Next thing we need to do is recall or retrieve the information that's necessary to do each one of those steps, each one of those 3 steps. So that is step A, we need the molar mass of aluminum. That's what we're going to use to go from mass to mole of anything. We always use the molar mass of that anything. In this case, it's aluminum. To go from mole to mole, we need the balanced chemical equation and the molar ratio contained in it. In this situation, since we're looking at aluminum oxide and aluminum, for every 2 moles of aluminum, we're going to be able to make 1 mole of aluminum oxide. And then finally, to go from moles of mass of aluminum oxide, just like before, anytime we're going between moles and mass or mass and moles, we need the molar mass. In this case, we need the molar mass of aluminum oxide. So we have our 3 steps. We just need to put them in the right order and do the solve. So we always start the same thing, what's given to us. And when we start with what's given to us of 124 grams of aluminum, we're going to go ahead and flip the first one so that we can have our grams of aluminum cancel. And then we're going to use step B. We're going to leave that the way it is so we can have our moles of aluminum cancel. And then for step C, we're going to also leave that one the way I wrote it so that we can have our moles of aluminum cancel. So it's all about the dimensional analysis, making things cancel. We end up with the only unit left on the board is the grams of aluminum oxide, which is what we're solving for. So we do the math, 124 divided by 26.9 times 1 divided by 2 times 101.96, and what we get is a mass of 234 grams of aluminum oxide. Could be formed when we take 124 grams of aluminum and react it with an excess of iron oxide. So what's that got to do with today? So we're going to make a twist. We're going to change one thing about this problem today, and that is we're going to identify how much of all the reactants we have. And that's where we have this idea of limiting reactants, or this concept of what's going to drive the reaction, what's going to limit the reaction, what's going to keep the reaction from going any further. The best way that I can help to describe or come to a conclusion as to what to do here is let's get out of the chemistry classroom for a second and let's step aside and go into a bicycle shop. So I have a bicycle shop, and in my bicycle shop, I know, and actually what I make in my bicycle shop, I make tricycles, is I have 10 frames, 27 wheels, 25 handlebars, 15 seats, and 2 pedals. And we're going to very, very, very generically, again, I'm not going to argue whether or not front wheels are different than back wheels and what's a handlebar. We're going to make this super, super simple. And we're going to say that in order to make a tricycle, we need 1 frame, 3 wheels, 1 handlebar set, 1 seat, and 2 pedals. And ironically, all those symbols are elements on the periodic table. And this big thing at the bottom is the formula for a tricycle. And the question would be, given what we have in our stockroom, how many tricycles can we make? Now I'm going to give you about 10 seconds to figure this out. So there's our bike shop, 10 frames, 27 wheels, 25 handlebars, 15 seats, and 22 pedals. How many tricycles can we make? Now, it's not going to be much of a stretch, but I gave you like 10 seconds there, and I bet you figured out how many tricycles we could make. Now, what did you do? Did you come up with 9? Did you come up with 9 tricycles? Because that's the correct answer. You could make 9 tricycles. And what did you do? In your head, very, very quickly, you said, well, with my frames, and I'm going to math it up with dimensional analysis, but this is what you did in your head, for frames, for every 1 frame, I can make 1 tricycle. So I could make 10 tricycles. With the wheels, I need 3 wheels for every 1 tricycle. So I can make 9 tricycles. And you immediately, probably your head says, that number is less than the 10, so I can't make a full 10. Then you did the handlebars quickly and you said that was almost a waste of time because the number was so large, but you still kind of did it quickly in your head and found that you could make 25 tricycles and crossed that out immediately. 15, again, 1-to-1 ratio, so you very, very quickly in your head figured that was a bad number, got rid of that. And then maybe you had to pause slightly, very, very slightly, very slowly on pedals to say there are 2 pedals for every 1 tricycle, and therefore you have 11 tricycles, and immediately cross that out of your head and says, well, that's too many. I can only make 9. And you came up with 9. And you did that quick. You did that in probably less than 5 seconds. Well, turn that into chemistry. Turn that into chemistry and dimensional analysis and that concept. That's exactly what you do with a limiting reactant problem. One of these materials runs out. One of these materials allows us not to be able to make any more tricycles. It limits us on the number of tricycles we make, and that's the number of wheels. The other 4 components we have in excess. We have more than enough frames, we have more than enough handlebars, we have more than enough seats, we have more than enough pedals, we have an excess. When we're done, when the reaction has stopped, when we stop making tricycles, we have all those components still in our bicycle shop. Those are in excess. So what we're talking about here is the concept of a limiting reactant. And a limiting reactant is whichever reactant, whichever starting component gets used up first. In our example of the tricycle shop, the thing that got used up first was the wheels. How do we know that? It was the one that gave us the least amount of tricycles, the least amount of product. So when we're trying to figure out which reactant is the limiting reactant, and we turn this into a chemistry classroom, we got to figure out which one of the reactants gives us the least amount of product, and that would be our limiting reactant. So let's go back to our problem. There was our problem. It says, what mass of aluminum oxide is formed when 124 grams of aluminum reacts with 601 grams of iron oxide? Well, we've already done one of the 2 reactants. We did, as part of our introductory piece, we did the 124 grams of aluminum, and we found that we could make 234 grams of aluminum oxide. So we did that one already. So let's check the other one. Just like we checked frames, then wheels, then handlebars, then seats, then pedals, each one in succession. We check each one of them to see how much product we can make. Let's check our iron oxide. So same thing as before. We start with a new given because now our given is the aluminum 3 oxide. Our unknown, we're still comparing it to the amount of aluminum oxide we can make because that's what the question is asking for. we still have to come up with a plan. Plan is going to be very, very similar. We're going to start with mass, but this time the mass we're going to deal with is the iron oxide. Go to moles of iron oxide. Go to moles of aluminum oxide. And then go to mass of aluminum oxide. So it's going to be very, very similar to the last one. So our plan looks nearly the same. The only difference is for the first step and the second step, we have a different starting compound. So for step A, we need the molar mass, but this time we need the molar mass of aluminum oxide. And hopefully I calculated that right, and I get 159.6882 grams of aluminum oxide per mole. Then step B, we're looking at aluminum oxide to iron oxide, and there's a 1-to-1 ratio there. And then for step C, it's the exact same from the previous example because we're talking about the same conversion of going from moles of aluminum oxide to mass. And just like the last example, we go ahead and solve. We start with our 601 grams of iron oxide, and walk our way across until we get, again, by canceling out, since we want to have our grams cancel, our moles cancel, our moles of aluminum oxide cancel, we're left with the grams of aluminum oxide. We get that I have 384 grams of aluminum oxide. So I have two answers. If I start with the aluminum, I get 234 grams of aluminum oxide. If I start with the iron oxide, I get that I can make 384 grams of aluminum oxide. So I get two numbers. So what do I do with those two numbers? Let's think about what we did in the bicycle shop. Did we pick the biggest number? Did we pick the smallest number? Did we add all the numbers together? Well, what we did in the bicycle shop is we figured out very quickly in your head in less than 10 seconds which one of the components gave you the least amount of bikes, and then you convince yourself that that was how many bicycles or tricycles you could make. So in this situation, it's the same. We're going to pick the smallest number, the 234 grams of aluminum oxide. This is how much we could make if we were to react 124 grams of aluminum with 601 grams of aluminum oxide. If we mix these together and allow these to react, we would make 234 grams of aluminum oxide by taking the aluminum and the iron oxide and reacting it together. So question, which reactant is the limiting reactant? Which reactant of the two, the aluminum or the iron oxide, gave us the least amount of product? Well, that was the aluminum. And which reactant, since there was only two, was the one that turned up in excess? When we were done, we had leftover iron oxide because it gave a larger value, meaning that when we were done, much like the frames gave us a larger value, and the seats and the handlebars and the pedals all gave us a larger value, that implies that those components were in excess. They were left over in our garage when we were done. In our reaction, when we're done here, the iron oxide is still going to be remaining in the container without any aluminum to react with it. Now, the last question actually comes back to a bit of a reality check with chemistry. Suppose I did this reaction. I took my 124 grams of aluminum and my 601 grams of iron oxide and reacted them together. And mix, stir, boom, a reaction takes place, but I only make 214 grams of aluminum oxide. What's my percent yield? Well, first you got to know what percent yield is. Well, it's percent, so we know you're going to get a percent number. Percent yield is like the grade. How'd you do? Okay. The official formula for percent yield is actual divided by theoretical times 100. Actual, how much did you really make? In this situation, we made 214 grams. How much should you have made? What's the theoretical yield? Well, I'm going to tell you, here's the funny fact of what we've done so far in stoichiometry. Everything has been theoretical. All of our values we've created, all of our values we've come to a conclusion of, were all calculated values. So even today, when we determined we could have formed from the reaction of the aluminum and the iron oxide, we could have formed 234 grams. That's theoretical. When you actually react them together, they only got 214 grams. So to get the percent or to get the grade, take 214 grams, actual, divide it by 234 grams, which was the theoretical, how much we could have made, how much the math told us we could have made, and times 100, and you find that this was a reaction that yielded 91.5% yield. Okay, so that's the two concepts that are associated with this video. Limiting reactants and what to do with that, and then percent yield. In your homework folder, shortly after I finish editing these videos, will be your homework for this week, and it consists of 6 problems. Actually, it's 3. You've got 3 problems, 3 limiting reactant problems, each of them followed by a percent yield question. So 6 problems. Same thing like the last couple homeworks, where you're going to print off what you have or do it on a separate sheet of paper, then take a picture of it or scan it and put it into your OneNote notebook. Okay, hopefully everybody can come to Teams one of the days this week. We're meeting on Wednesday and Thursday this week. Everybody, please stay safe, stay healthy, practice that social distancing. I'm going to get on my little political bandstand. The virus is not gone, people, just because the governor has opened the, allowed you to no longer have to stay at home. Keep your distance from people, keep your distance, do as best you can to stay separated from people. You never know who next to you, what Yahoo next to you may have the virus, in which case it spikes again. I don't want us to do that. I would love to be able to see you guys as quickly as possible come fall. So the quicker you guys continue to comply with your stay at home or stay socially distant, the better off it is. There's my political little spiel. It's not dead, guys. It's just because the governor says everything is good doesn't mean everybody is a clean bill of health. There still is a lot of people out there catching the virus, and there's a lot of people out there dying from the virus. I don't want it to be any of you guys, and I don't want it to be anybody else in Carroll County, so that we have to continue this craziness of distance learning. Have a great day on that really, really somber note. I will see you in Teams this week again. We're meeting on Wednesday and Thursday. Have a great day. Toodles.